Okay. So the structure of the class, we'll just go over, I think, 5 questions from homework. And then I have a few varsity tutors discrete questions. And then we will do some brief content review and then go through a practice passage in real time from Khan Academy. So um, if you have any questions along the way, feel free to stop, feel free to drop them in the chat, whatever makes you, whatever way you prefer. But also remember, you can reach us out, you can reach me specifically or any of the tutors afterward if you have a question. Yeah, okay, so let's get started. So this is the content that is kind of on the schedule for today. So I think Isabel just went over biologically important molecules in terms of, I think, proteins and amino acids. So this class is focused on primarily sugars, and then I just have 2 slides on lipids. So we'll cover, some key structures of sugars and how to name them and what type of kind of terminology might come up. And then stereochemistry, mutarotation, reactivity, and then a couple important tests. And then we'll just briefly go over lipid naming and kind of importance of or important features of biologically important lipids. Okay, so if anybody has any specific questions on the homework, feel free to drop them in the chat. Otherwise, I will just go through 5 questions that I've picked. Again, if you don't want to ask a question now, you can always ask it later through Slack or email, so no pressure. So the way I'll do this is I'll put the question up, and if you want to drop answers that you picked in the chat and we can discuss them, or if you want to explain, feel free. Otherwise, I'll just give you a few seconds and then I'll go over the answers. So the first one was kind of just a terminology question, but which of the following molecules is a furanose in its cyclical form? Any ideas? Okay, so the answer here is fructose. And so one important thing to note right off the bat is that sucrose and lactose are both disaccharides. So you can kind of eliminate them right away, but fructose, and I'll show the structure of a furanose later, but basically a furanose is kind of looks like a pentagon as opposed to a hexanose or a purinose. A furanose looks like a pentagon, kind of roughly, as opposed to a purinose, which looks kind of like a hexagon. So fructose exists in it looks like a furanose in cyclical form. Okay, so which of the following describes the relationship between straight chain forms of D-glucose and galactose, given that they are non-cyclic molecules that differ only in stereochemical configuration at the 4th carbon? Any ideas? If not, so they are epimers. So this is again kind of a definition, but a lot of this lesson is kind of, keeping definitions straight and keeping structure straight and knowing kind of if you were to get a question about an epimer, what that means. And essentially this question stem kind of defines what an epimer is. So epimers are a specific type of diastereomer. Basically, it refers to molecules that differ in stereochemical configuration only at one specific. Oh, so somebody just said D. What is D? So D refers to anomer, refers to the anomeric carbon, and we'll go over what that is. But anomeric carbon is carbon 1. And so that's when you'll see like alpha and beta. So you'll hear about like alpha, 1 to 4 linkages in the start, right? And that's referring to the anomeric carbon being alpha or beta. And I will go over that. Again, this is a really terminology heavy class. And so yeah, feel free to drop those questions because I think it's helpful to kind of confront them as we go along, and then that way I know what might be useful to spend a bit of time on later. Um, so enantiomers, remember, if we're looking at like the other answer choices, meso compounds have a plane of symmetry. So that would not relate to D-glucose and galactose. Enantiomers would differ at every single chiral center. Epimers differ only at one, and anomers would refer to like the anomeric carbon, which again we'll cover in a bit. Okay, I'll go on to the next one. So this one is a bit long, so I'm not going to read the whole thing to you, but basically it says you have an IR spec and you see two separate peaks, and based on this data, which of the following molecules was the likely the original sample? Any ideas? So this one is, I think, a good question because it combines kind of a few principles or a few things that you should know. So in this case, um, basically, I'll start from the like actually a little bit later, but I'll start from right here. So because there's two separate peaks in this region that's listed, that basically tells us that there's two different carbonyl groups. So this region of IR spec is associated with carbonyl functional groups. So if we have two separate peaks, it means we have two different carbonyl functional groups. So because we're talking about sugars, and we'll talk about, aldoses and ketoses a bit more, but essentially we're talking about sugars. So it would be safe to, kind of, we would know that this means that we have essentially an aldose and a ketose that are contributing to our disaccharide. So we can eliminate fructose right away. And I think then maltose is, I think, the combination of two glucoses. So um, that would not be two separate peaks. So we're down to lactose and sucrose. And lactose would also not be two separate peaks because it is glucose plus galactose, which would mean they're both aldoses. So you would again get one peak. So sucrose, we can basically try out. And we know that sucrose is glucose plus fructose. And so that would make sense because glucose is an aldose and fructose is a ketose. Any questions on that? Okay, so next one, basically how many glucose molecules are created in the cleavage of glycogen and amylopectin? So this one is mostly just testing whether you know what makes up glycogen and amylopectin. Both of them are made up of glucose. So if each are made up of 100 monosaccharide subunits, all of those monosaccharide subunits are glucose. So you get a lot of glucose. So 200 molecules. Okay. A deficiency of oxaloacetate would most likely increase the catabolism of what potential energy source? Any ideas? Mm. Yeah, so uh close. So you're close in that like you would want to make something that can kind of feed into um basically metabolism. So you want to, in this case, you would make a Krebs cycle intermediate. So if you have a deficiency of oxaloacetate, remember oxaloacetate is a Krebs cycle intermediate. So essentially, you want to use something to make kind of that Krebs cycle intermediate, and that would be C glucogenic amino acids. So remember that glucogenic amino acids basically can be transaminated to turn into kind of a Krebs cycle intermediate, and then that would essentially supplement this oxaloacetate deficiency that you're trying to treat. Any questions on that? Okay. So let's do a few questions just together. So the first one is, which of the following is true regarding saturated and unsaturated fatty acids? And I know they don't have letters, but let's just assume this is like A, B, C, D. So any ideas for this one? Okay, for the sake of time, I'll just click. So the answer was B. So a 15 carbon saturated fatty acid has a greater molecular weight than a 15 carbon unsaturated fatty acid. So um, this is true. So remember that a saturated fatty acid has an extra hydrogen. So essentially, because it is lacking, because what makes an unsaturated fatty acid unsaturated is that it is basically not completely saturated with hydrogens, and that is because it has a double bond. So a saturated fatty acid essentially has an extra hydrogen. So there's not a great difference in molecular weight, but it does have a greater molecular weight than an unsaturated fatty acid. And so then obviously this would completely contradict D. So you could also rule out D. And then C is not true. So they would have the same amount of oxygen atoms. So B is the best choice. Okay, which of the following statements is true concerning glucose polymers? Yep. So somebody said B and B is correct. So um, B is just true. So cellulose is essentially made up of a bunch of glucoses linked with beta 1 to 4 linkages. And we'll go over that later. But humans don't have an enzyme to break down those beta linkages. But that doesn't mean that we don't eat foods that contain cellulose. So D is wrong. And A, maybe you looked at A. A initially might strike you as attractive, but starch is held together by an alpha 1 to 4 linkage. So it's just keeping those linkages straight. So starch is alpha 1 to 4, and cellulose is beta 1 to 4. And again, we'll go over that. Okay. Which of the following describes a beta oxidation reaction? Mm, A, yep, and A is correct. So, I've listed out the steps here, but this isn't super pertinent for today, but I just wanted to remind you of how fatty acids are connected kind of to metabolism and keeping the broader picture in mind. So, beta oxidation happens in 4 steps. So, you oxidize the fatty acid and you make a double bond, and then you hydrate that double bond to make a hydroxyl group. Then you oxidize that, and then you essentially split it, and you split off an acetyl-CoA. So, but the short version is that we start with a fatty acid and we end with a bunch of acetyl-CoAs. So, the right answer would be A. Okay, so if you have any specific content you would like to go over, feel free to drop it in the chat. Otherwise, I will just plan to spend about the next 25 minutes going over slides. And if it doesn't take that long, then we'll just kind of go through. But otherwise, I'll plan to start a practice passage at around 11:40, 11:45. Okay, so we'll start with sugars and just like the basic structure. So, the most basic structural unit is a monosaccharide. So, a monosaccharide meaning basically like one, so one of these. So, D-fructose is an example of a monosaccharide, glucose, galactose, mannose, etc. So, a monosaccharide with 5 carbons would be a pentose. A monosaccharide with 6 carbons is a hexose. Kind of makes sense. 5 pent, 6 hex. A monosaccharide with a ketone functional group is a ketose. Um, so an example of a ketose would be fructose. And then a monosaccharide with an aldehyde functional group is an aldose. So like the remaining 3 here would be aldoses. So remember, they follow like normal naming conventions. So carbon 1 is the carbonyl carbon here. Um, So it's either the aldehyde or the ketone group. So this is carbon 1, and I think, yeah. And that's kind of the basics of these structures. So one thing to notice here is that if you look at glucose and then you look at galactose, they differ only at this carbon right here. So that makes them epimers. And then the same between glucose and mannose. So they differ only here. So they're also epimers. But then if you look at galactose and mannose, they differ at 2, right? So they are not epimers. So that's a good kind of just check on that first question that we did. Okay. So there's a lot of naming things for sugar. So this is kind of the basics of their formula and how they're put together. But then there's also stereochemical naming conventions as well. So remember that stereoisomers are compounds that have the same chemical formula but differ in the spatial arrangement of component atoms. So then you have enantiomers, which are non-superimposable mirror images. So they would differ at stereochemistry at every chiral center. But then we talked about this already, but epimers differ in stereochemistry at exactly one chiral center. Okay. And then there's also the D and L naming conventions for sugars. So, and I mean for biological molecules more generally. But basically, these sugars are named based on glyceraldehyde. So if you look at them in a Fischer projection form, if the OH after the carbonyl is to the right in a Fischer projection, that makes it a D sugar. And that is based off of glyceraldehyde, which is why I have glyceraldehyde on this slide. So if you look back at this last slide, if we look at glucose, this OH is to the right, which makes it D glucose, although they're also listing these as D, so I will double check this for you. But L-glyceraldehyde is right here. So it actually, let me just double check something. I think so. It's actually, I think, based on the CH2OH. So that's my bad. I'll fix that. Because it's to the right of the CH2OH. That's why it is D. So it's based off of this alcohol group. So if you look back, every single one of these, the OH is to the right on the carbon immediately adjacent to the CH2OH. So that makes them D. And I will fix that on the slides. But then the opposite is true essentially for L. So if you were to flip all of these OHs to this side, that would make them all L. Okay. So the next thing is basically understanding how sugars go from linear or like chain form into a Hay. So this is a Fischer projection. This is a Hayworth projection. So essentially, you have a chain of 6 carbons, and we know that 6 carbon rings are particularly stable. So you can have an intramolecular reaction where this OH group kind of attacks the carbonyl. And we know that this carbonyl carbon is typically relatively electrophilic, so it makes sense that it would be subject to nucleophilic attack. So this OH group can kind of attack this carbonyl, and then this pops out. And essentially, you get a bond formed between carbon 1 and carbon 5. Um, or carbon 1 and carbon 5 become linked through this O, if that makes sense. So this structure is kind of just representing that. But then the way to remember basically how you convert from this structure to this one is downright uplifting. So anything that is on the right-hand side of this line goes down in the Hayworth projection. So you'll notice I put a star by 1. That's because 1 is the anomeric carbon. So we're going to ignore that one. But if we go to 2, the OH group is on the right, so that means it goes down. 3, it goes up. 4, it goes down. And then 5, we it 5 is kind of unique, but like 2, 3, and 4 go downright uplifting. So that's how you convert. This carbon is special because of mutarotation, which we will talk about. So that's why I've just drawn it as CHOH. That basically this OH group can be either up or down, and that's what determines whether a sugar is alpha or beta. Okay, so when we're naming a cyclical structure, if it's this 5-carbon structure, it would be a furanose, and then if it's 6-carbon, it would be a pyranose. And you'll notice you might be like, where did this, or not a 6-carbon, but a 6-membered ring and a 5-membered ring. They're all 6 carbons. So 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. But the kind of like hexagonal one is a pyranose and the pentagonal one is a furanose. Okay, so basically sugars. So I have a star by this alpha carbon. So these sugars are examples of hemiacetals, and so essentially they will spontaneously convert between the open form and the closed form, shown here. So this form and this form um, go rapidly back and forth. And so because of that, this carbon that is being attacked, its stereochemistry is essentially much less locked in place than the rest. So this OH group can be either up or down. It's not locked kind of into either conformation the same way that carbons 2, 3, and 4 are. So this means that this orientation changes between alpha and beta. So this is the anomeric carbon. So this is when we're talking about anomers, we would be referring to this carbon specifically. So alpha carbons, the OH is down, meaning below the plane, and a beta one, the OH is up. So that is also where you get the description of those linkages. So if you have an alpha 1 to 4 linkage, it means that you have, and I'll show a picture of this, but it means that you have this glucose, right? The OH is down and it's bonding to another glucose's carbon 4 with their OHs. And so when you see it in picture form, it's kind of like the O is sitting below the plane, and that's how they're bonding. Okay. Any questions so far? Okay, I'll keep going just for sake of time. Okay, so like we just said, all of these carbon or all of these sugars will spend some time in chain form, basically. So aldehydes, then anything that's spending time in chain form. So an aldose might spend some time in its chain form, in which case it would have a free aldehyde group. So that aldehyde group is essentially not special. It can be oxidized just like any other aldehyde. And in that case, it'd be oxidized to a carboxylic acid, right? So because the sugar can itself be oxidized, it is a reducing agent. So we refer to these sugars as reducing sugars. And I'll just say that again because I think people tend to have I mean, people, including myself, tend to have trouble keeping this straight. So because the sugar can be oxidized to a carboxylic acid because it's an aldehyde, because it itself can be oxidized, it helps other things get reduced, which makes it a reducing agent. And that's why we would call it a reducing sugar, even though the sugar itself is oxidized. Um, so there's two reagents which check for reducing sugars. So I think kind of the specifics of these reactions are beyond the scope of the class for an hour, but you have Benedict's reagent, and that produces a red precipitate. And then there's also Tollen's reagent, which produces silver oxide. And I would just, if you're looking for a fun way to remember these things, you can look up a video of somebody doing a Tollen's test. It's quite fun. It produces like a bunch of silver that coats the inside of the flask that it's done in. So it's kind of a fun one to see. But they're both obviously like very visible effects. So if you have a sugar and you don't know what it is, you can do these tests to see if it's a reducing sugar, which would be a sign that it's an aldehyde or an aldose, right? Um, yeah. Any questions on any of that? Okay, so sugars form glycosidic bonds. So hemiacetals, which remember when we talk about a hemiacetal, we mean like this is an example of a hemiacetal. So hemiacetals react with alcohols to form acetals. So the anomeric hydroxyl group, the hydroxyl at C1 attacks an alcohol to form an alkoxy group. So that would mean, for example, this alcohol can essentially act as a nucleophile, and you can substitute in an alkoxide, like an alkoxy group. So you don't just have CHOH. So the result is a carbon-oxygen bond, and that is called a glycosidic bond. So you probably most commonly see glycosidic bonds between monosaccharides to make disaccharides and then polysaccharides. So again, that's what we're talking about when we say like an alpha 1 to 4, that's a glycosidic bond. So glycosidic formation is a dehydration reaction. And that should make some sense because if you look at this, if you kind of like attack something else, you can eliminate a water with this H and this H. You can make a water. So you dehydrate to form the glycosidic bond. So then when you try to break it, you put water in and you hydrate. And that also means that you cleave the water, right? Because you put water in and then water breaks apart and the two molecules break apart. So let's look at some examples. So here I've put a couple disaccharides. So you can see this is what I was saying before when we have an alpha to like an alpha bond. So in this case, this OH, there was originally an OH here that was below the plane, and then there was another OH here. And then, one attacks the other. And so you then get both of them kind of bonded below the plane. So this is an alpha one. And then in this case, there was one that was above the plane and one that was below the plane. So it looks like this. So this one, because the one on the left was below the plane, that would be alpha. So yeah, and then this one is beta because it's above the plane, and then alpha. And that you can see that down here. It goes alpha, beta, alpha. And then this might be a good example too of how this is a dehydration reaction, because if you think originally you would have had an OH over here and an OH over here. So you have two O's and two H's, and you end up with just one O. So you've eliminated an H2O. So you've eliminated a water. So in terms of naming, you name the configuration of the anomeric carbon. So in this case, you would say alpha 1 because it's carbon 1, and it is alpha, and it is bonding to carbon 2 of fructose. So it's an alpha 1 to 2 linkage. If there are two anomeric carbons involved, you would have to say both of them. So you would have to say like alpha, alpha 1 to 1. So I mean that both of them were alpha. But you also see here like you have lactose, so that's a beta 1 to 4. So galactose beta 1 to glucose 4. Okay. Any questions on naming or any sugars? Okay. So then we'll just quickly talk about polysaccharides. So we talked briefly about this before, but cellulose is essentially a bunch of glucoses linked together, and they're linked through beta 1 to 4 bonds. So that would be the anomeric carbon. It would be above the plane. Okay, so cellulose is beta 1 to 4, and humans don't have the enzyme to digest the beta 1 to 4 bonds. And then amylose, which is basically starch, they are linked with alpha 1 to 4 bonds. Can break those down. So amylopectin is essentially starch, but it has also alpha 1 to 6 branches. But they are less common in amylopectin than glycogen. So the ones that we're mostly concerned with are basically all glucose. So then the important thing to remember is that you go from amylose, which is kind of basic alpha 1 to 4, just a very long chain, and then you add branches, and then glycogen is even more branched. Okay, any questions? Okay, so we just have very brief mention of fatty acids. So just a reminder, fatty acids are essentially just long chain carboxylic acids. So obviously you have your carboxylic acid end here, and then you just have a long chain of carbons. So saturated fatty acids, again, they're saturated because they're saturated with hydrogens. They have no double bonds and they're long chain. And then unsaturated fatty acids are not saturated with hydrogens, and that's because they have a double bond. And so generally speaking, like saturated fatty acids, because they are saturated, can pack more tightly together. And that's why you see things like butter or even like coconut oil are more saturated fats. And so they are solids at room temperature. And then unsaturated fatty acids, because they have this like kink thrown into them because of their double bond, tend to be liquids at room temperature because they can't pack as closely together. Okay. So then the last thing that I just wanted to show the structure of is triacylglycerols, or like tags. So a good structure to know is the structure of glycerol, and obviously it's kind of a basic structure, just 3 carbons, and you have your OHs. But if you look at glycerol and you look at fatty acids, a very easy way to store fatty acids is in triacylglycerols, because you can essentially do a quick esterification reaction with this carboxylic acid and this alcohol group. And then again, this would be a dehydration because you're going, if you look, you have, 2 O's and 2 H's. So you would subtract an H2O and you would esterify it. And so you can store fatty acids in triacylglycerol form, essentially. Okay, so we have almost about a perfect amount of time. So I have here the practice passage for today. So I will give you all, I think let's do 8 minutes. So the passage is 5 questions, and I will get the link and put it in the chat. Just give me 1 second. I'm going to set a timer for 8 minutes. So I will put the link in the chat, and then we can meet back to discuss it in 8 minutes. Okay, so I think it's been about 8 minutes, but we can come back together. So the first question was carbohydrates. Sorry, this is just a repeat. So, when two monosaccharides are joined by the nucleophilic attack of one sugar's hydroxyl group on the other sugar's carbonyl carbon, the result is a disaccharide containing a glycosidic linkage. What would be the molecular formula of a disaccharide made from 2 units of glucose? Any ideas? Okay, so the answer here is A. So remember that glucose would have a formula of basically it's a carbohydrate. So glucose has a formula essentially of like 6 carbons plus 6 waters. So each carbon is hydrated. So glucose itself is C6H12O6. But then remember when you're putting 2 units of glucose together, you subtract 1 water, right? Because it's dehydration reaction. So you would basically have C12H22O12 minus H2O. So that leaves you with A. Does that make sense? Any questions? Okay, so an aldohexose has how many units of unsaturation? Okay, the answer here is 1. And importantly, the number of units of unsaturation doesn't change even when you flip from like linear or chain form to ring form. So in linear form, you would have a double bond. So that single double bond at the carbonyl carbon contributes 1 unit of unsaturation. And then when you convert into ring form, because you're in a ring, that gives you 1 unit of unsaturation. So either way, an aldohexose has a single unit of unsaturation. Okay, I'll keep going. So, which molecular stereochemistry describes D-glucose? Okay, so the answer here is D, and I'm going to go back to our original slide with D-glucose on it. It is right here. So if we're looking at D-glucose, anything that is to the right in a Fisher projection is going to be R, and anything to the left is going to be S. So for D-glucose, we have carbon 1, carbon 2 is going to be R, carbon 3 is going to be S, and then 4 and 5 are both going to be R. Um, and then let me just go back to our slide. So that's here. So, but that is how it's assigned. So anything to the right in a Fisher projection is going to be R, anything to the left is going to be S. Okay. Which mechanism best describes the opening of glucose's ring structure? Any ideas? Okay, so I've covered this quite a bit, but it's an important concept. So remember when you're making your glycosidic bond or when you're making the bond to make the ring, you are losing a water because you're taking this OH and you're going to attack. So remember, imagine you'd have an OH here and an OH here, so you would attack and make this bond, and then you would you'd lose a water. So when you are making the ring, you take out a water. So if you're trying to break the ring back open, you would put a water in. So it'd be a hydration reaction. Okay. And then the final, I think the final question is, what is the mass percent of oxygen in beta D glucose? So for this one, the answer is 53%. So this is kind of a good Gen Chem review. So again, our formula of glucose is C6H12O6. So then if we're looking for the mass percent of oxygen, we need our molecular mass of glucose. So it'd be 6 times 12, so it's 72, plus 12 is 84, plus 96. So 84 plus 96 is 180. Um, and then we have the amount of oxygen divided by that total. So our amount of oxygen is 16 times 6, which is 96, um, over 180. So if we're looking at our answers, one thing I like to do when doing math for the MCAT is just checking how the answers compare to each other. So in this case, we kind of just need to know one thing right away that's easy to tell is whether it's over or under half. So we can immediately eliminate A and B, and then between C and D, we know that it's kind of closer to 50%. So 53% is the right answer. I mean, you can also do the math, but um, that's a good way to kind of guide you to kind of narrowing it down so that you're worried about less answers. Yeah, so the right answer there is 53%. Okay, so that is all I have for today. So I'll give you guys a few minutes of your day back. But if you have any questions, feel free to email or send either the group a message on Slack, or I think you should be able to also just message me on Slack. I will fix one thing in the slides, but then this recording will be uploaded to YouTube and you can get the link to rewatch it. And you should also have access to the slides. So if you have any issues reaching any of the resources, just let us know so that we can get them to you. Um, and yeah, if you have any other questions, I'll stop recording now and feel free to ask them. Otherwise, have a good rest of your Sunday, and our inboxes are always open.